Hello students, today in our session, I know you all are studying with this third lesson, magnetism and magnetic effects of electric current hardly. Now this is the session number 5 and today we are going to see the topics magnetic properties and classification of magnetic materials. Now let's see what are the magnetic properties. All the materials we use are not magnetic materials. All the magnetic materials will not behave identically. In order to differentiate one magnetic material from another, we need to know some basic parameters. The first parameter is magnetizing field. The magnetic field which is used to magnetize a sample or specimen is called magnetizing field. Magnetizing field is a vector quantity and is denoted by H vector and its unit is AM minus 1. Next one, magnetic permeability. Can you tell me what you mean by this permeability? I already explained you a lot of things about this permeability. Okay, let me explain. The meaning of magnetic permeability means, let me explain in Tamil to understand. Kanda Udurval or Kanda Utpugu Thiran. Okay? Yeah. Now, magnetic permeability can be defined as the measure of ability of the material to allow the passage of magnetic field lines through it, or measure the capacity of the substances to take magnetization or the degree of penetration of the magnetic field through the substances that I already mentioned. Kanda Udurval or Kanda Utpugu Thiran. Relative permeability. This is tagged with our magnetic permeability. The relative permeability mu r is defined as the ratio between absolute permeability of a medium to the permeability of a free space. Here mu r is equal to mu by mu naught, and mu naught is the permeability or absolute permeability. Mu is the permeability any medium it is denoted. Relative permeability is a dimensionless number and which has no units. Then intensity of magnetization. What do you mean by this intensity of magnetization? In Tamil we used to translate it as Thivira Kanda Mayamakkal or Kanda Serivu. Okay. Actually, you know what do you mean by this Thivira Kanda Mayamakkal? It is an intensity. It is a mode of application along the magnetization. When a material is kept in an external magnetic field, atomic dipoles are created. Hence, it will try to align partially or fully along the direction of external field. The net magnetic moment per unit volume of the material is known as intensity of magnetization or magnetization vector or magnetization. Which is termed as m vector is equal to magnetic moment divided by volume, which is equal to 1 by v into pm vector. Now the SI unit of intensity of magnetization is ampere meter minus 1. For a bar magnet, the pole strength Qm, the length 2L and area of cross section A, the magnetic moment of the bar magnet is an volume of the bar magnet, that is Pm is equal to Qm 2L. Now the intensity of magnetization of a bar magnet is V is equal to A 2L modulus, which is termed as 2LA. So M vector is equal to magnetic moment by volume is equal to Qm 2L vector divided by 2L. You can cancel this 2L and 2L. So Qm by A. And in magnitude, the equation M vector modulus is equal to M is equal to Qm into 2L. You can cancel this 2L. So M is equal to Qm by A. This means for a bar magnet, the intensity of magnetization can be defined as the pole strength per unit area. That means the phase area. The fourth one, magnetic induction or total magnetic field. When a substance like soft iron bar is placed in a uniform magnetizing field, H vector, it becomes a magnet, which means that the substance gets magnetized. The magnetic induction, that means the total magnetic field inside the specimen, is B vector, which is equal to the sum of the magnetic field B vector produced in vacuum due to the magnetizing field and the magnetic field due to the induced magnetization of a substance. Here B vector is equal to B vector naught plus Bm vector, which is equal to mu naught H vector plus mu naught I vector, or B vector is equal to B naught plus Bm, which is equal to mu naught H plus I vectors. Last one, magnetic susceptibility. When a substance is kept in a magnetizing field, the magnetic susceptibility measures how easily and strongly a material can be magnetized. So let me explain this magnetic susceptibility in Tamil. Kanda unar thiran alladu Kanda erpu thiran. Okay, so accepting the magnetism. It is defined as the ratio of intensity of magnetization M vector induced in the material due to the magnetizing field H vector. So Xm is equal to M vector divided by H vector. It is a dimensionless quantity. Now, classification of magnetic materials. How do you classify the magnetic materials? See, magnetic materials are generally classified into three types based on the behavior of materials in magnetizing field. They are diamagnetic, paramagnetic, ferromagnetic materials. Now, let's see what are they and what are the properties of that materials. First of all, let's see the diamagnetic materials. See, this is an example for diamagnetic material, which is used to alleviate the trains. When placed in a non-uniform magnetic field, the interaction between induced magnetic moment and the external field creates a force which tends to move the material from stronger part to weaker part of the external field. Here you can see we create an external magnetic field in between these two magnets, and it is move the material from stronger part to the weaker part of the external field, Now it means that the diamagnetic material is repelled by the field. This shows the repulsion in between the magnetic fields. This action is called diamagnetic action, and such materials are known as diamagnetic materials. Now the examples of diamagnetic materials are bismuth, copper and water. So what are the properties of diamagnetic materials? They have some peculiar properties which is compared to ferromagnetic and paramagnetic. First one, magnetic susceptibility is negative. Relative permeability is slightly less than the unity. Third one, the magnetic field lines are repelled or expelled by the diamagnetic material when placed in a magnetic field. I show an example for you in this. Then fourth one, the susceptibility is nearly temperature dependent. See here in this picture you can see the diamagnetic materials, if it is the temperature is greater than the temperature of coefficient, it travels towards the material. If the temperature is less than the temperature of coefficient, then it deviates from that material. This shows the Meissner effect of the diamagnetic material. Meissner effect is called the superconductors are perfect diamagnetic materials. The expulsion of magnetic flux from a superconductor during its transition to the superconducting state is known as Meissner effect. That means a conductor is transferring from a conductor which have a magnetic material or magnetic field is transferring its nature from conductor stage to superconductor stage is known as the Meissner effect. The transition is known as Meissner effect. Magnetic leviated train are a best example for this Meissner effect and diamagnetic materials. Magnetic leviated train is also called as maglev train, which is usually a normal transport system in Japan, China and other European countries. This train floats above few centimeter from the guideway because of electromagnet used. Maglev train does not need wheels and also achieve greater speed. You can see here there is no wheel inside this train. Okay, and here the maglev train is composed with magnets with the two sides, and this is north and south poles mentioned here. The basic mechanism of working of maglev train involves two sets of magnets. One set is used to repel, which make the train to float above the track. See here, it is used to float above the track. Then another set is used to move the train floating ahead at a very great speed. These trains are quieter, smoother and environmental friendly compared conventional train and have potential for moving with much higher speed with technology in future. And in India we are going to install all these maglev type trains in near future, probably after 5 years. Next one is paramagnetic materials. What are the paramagnetic materials? When magnetic materials, when placed in a non-uniform magnetic field, the paramagnetic materials will have a tendency to move from weaker to stronger part of the field. Materials which exhibit weak magnetization in the direction of the applied field are known as paramagnetic materials. Some examples for this paramagnetic materials are aluminum, platinum, chromium, etc. The properties of paramagnetic materials. Slightly difference between the diamagnetic and paramagnetic materials in these properties. See, first one, the magnetic susceptibility is positive and small. Relative permeability is greater than unity. The magnetic material field lines are attracted into the paramagnetic materials when placed in a magnetic field. The susceptibility is inversely proportional to the temperature. I already explained you about this permeability and susceptibility in the last class. So I think you all know about. In accordance with this paramagnetic material, we have to define a new law which is derived by Curie, which is it is called Curie's law. When temperature is increased, thermal vibration will upset the alignment of magnetic dipole moments. I think you all know what do you mean by this magnetic dipole moments. We saw the magnetic dipole moments in earlier classes, particularly in axial line and equatorial line. Okay, so the magnetic susceptibility decreases with increase in temperature. If the temperature increases, then it upsets the alignment of magnetic dipole moments. In many cases, this susceptibility of the material is Xm proportional to 1 by T or Xm is equal to C by T. Now you can see there is a graph which is between the Xm and T. If the magnetic susceptibility decreases with increase in temperature, if the temperature increases like this, then there is a upset alignment of magnetic dipoles. So this relation is called Curie law. Here C is called Curie constant and temperature T is in Kelvin. Now let's see the ferromagnetic materials. The direction of magnetization varies from domain to domain, and thus net magnetization of the specimen is zero. In the presence of external magnetic field, two processes takes place. Let me show the domains which are randomly aligned. See, the domains are randomly aligned, but they are in different directions, not in same directions. If the domains are aligned with the external field, then it's all placed in same direction, towards the same direction. The two process which takes place using the external field is aligned means, first one, the domains having magnetic moment parallel to the field grow in size. You can see the field grow in size. Then the other domains which are not parallel to the field are rotated so that they are aligned with the field. You can see they are aligned with the field. So when these domains having their magnetic moments which are parallel to the field are placed in a non-uniform magnetic field, the ferromagnetic materials will have a strong tendency to move from weaker to stronger part of the field. Materials which exhibit magnetism in the direction of applied field are called ferromagnetic materials. Like this, the materials are exhibit strong magnetization in the direction of the applied field. This is the direction of the applied field. Some examples of ferromagnetic materials are iron, nickel and cobalt. Now the properties of ferromagnetic materials. First one, magnetic susceptibility is positive and large. Relative permeability is also large. The magnetic field lines are strongly attracted into the ferromagnetic materials when placed in a magnetic field. The susceptibility is inversely proportional to temperature. Next one, let's see the Curie-Weiss law. As temperature increases, the ferromagnetism decreases due to the increased thermal agitation of the atomic dipoles. At particular temperature, the ferromagnetic material becomes paramagnetic. This temperature is known as Curie temperature. See, there are the properties between the ferromagnetic and the paramagnetic are resemble each other. There is a connection in between this para and ferromagnetics. Here I show one graph for your reference. In this graph you can see the susceptibility of a material above the Curie temperature is given by Xm is equal to C by T minus Tc. That means this is Xm and this is T. T is the maximum temperature and this is the temperature quotient, and which is we can to find this we have to take T minus Tc, and this relation Xm is equal to C by T minus Tc is called Curie-Weiss law. The constant C is called Curie constant and the temperature T is in Kelvin. So Xm is multiplied into T greater than Tc, which is equal to mu naught into C by T minus Tc. Now let's differentiate the dia, para and ferromagnetisms. First of all, this is the types of magnetism. Let's see what is the difference between these three magnetism. In magnetizing field is absent, that means H is equal to 0. If the magnetizing field is absent, then we will have a zero magnetic moment in diamagnetism, and if the magnetic field is absent, net magnetic moment, but it have a random alignment here in para, and the net magnetic moment in a domain but random alignment of domains in the ferromagnetism. See, the magnetic field is present, that means H is not equal to 0. Then in diamagnetism, aligned opposite to the field, you can see it has been aligned opposite to the field. But in paramagnetism, it is aligned with the field, and in ferro also it is aligned with the field. Third one, magnetization of material. You can see different graphs for magnetization material, which is opposite to the magnetism and magnetic field. Here it resembles that. The susceptibility is negative in diamagnetism, positive and small in paramagnetism, positive and large in ferromagnetism. The relative permeability, it is less than the unity in diamagnetism, greater than unity in paramagnetism, and it is very large in ferromagnetism. Thank you students, study well.